we ready to go? Okay. Now that we have the web page public again, we can proceed. Yes, it is turned on, unless the batteries are dead. We're good. All right. All right. We're good. So what I want to do now is look at the windmill data. And first we just go ahead and regress y on x. And we see the residuals for the transform windmill data, they seem fine. Okay. But as we saw, well, actually, do they look fine? No, that's for the transform windmill data. No wonder, they don't look fine. The residuals for a simple linear regression of the windmill data is this. What is the windmill data? Example 5.2. You can't see it. Example 5.2. You have a research engineer is investigating the use of a windmill to generate electricity. He has collected data on the DC output from his windmill and the corresponding wind velocity. So there's wind velocity, which is the regressor. And I didn't do the fit, but the actual scatter plot of the data here on this worksheet. I'm only looking at the residuals. We already looked at the scatter plot of the data, okay, which had the wind velocity was the regressor, and then you had the output, DC output, as the dependent variable, okay, which was bending downwards. Apparently, the more velocity you get, I mean, you could have like, hurricane, you still wouldn't get that much energy. Actually, the thing would break, right? Perhaps. So there's only so much you can get. So the regression function is not a linear function of the regressor, apparently. But it may be that with a transformation in the x variable, that the model is transformably linear or intrinsically linear. What does that mean? I mean, it's not a linear function of x, but you still have linear dependence on regression coefficients. What would be an example of that? The example of that the author just pulls out of the hat, so to speak, is that, well, suppose the windmill data was approaching a horizontal asymptote here, okay? And so this was y and this was x. And let's say the constancy of variance was not the trouble, okay? It's just what's the right regression function? What's the right curve here? Okay? And what I want is I want a regression function still is linear in the parameters. Okay, do you know any functions that are linear in the parameters that does have a behavior like that? A function of x? Okay, something like beta 0 minus, plus beta 1 times 1 over x, where you would have a negative on the beta, right? Is that right? Or, where beta 1 is negative. Okay? I think that does come down like that, or does it? Yeah. For x greater than or equal to a certain amount. Okay, for not x, all the way to x equal to 0, for x greater than or equal to 1 or something like that. Okay? Okay? So we'll start off with beta 0 minus beta 1, plus beta 1 if beta 1 is negative. Beta 0 minus something, and then less minus something, and less minus something, okay? Until you finally get beta 0 as the asymptote in here, okay? Okay. Okay, so that's one thing, and so you could just try that. Now, is there some other reason that you might not do that? Is there some way, what if I had beta 0 plus beta 1 times 1 over the square root of x? Wouldn't it also behave like that? It would behave exactly the same. qualitatively, it would still have an asymptote, okay, at beta 0. So what's the right power for x, you might ask? So what the author does, I didn't even show that on this particular worksheet, is just go ahead and put in the power 1 over x. So I could do that on a separate sheet, or maybe just do it on this sheet on a later section. So I'll just take this. I'll take velocity x and I'll take the DC output. Well, then I'll also take the DC output here, y. Okay. Okay, and I'll just go ahead and make that transformation in x. I'll go ahead and make a 1 over x. So let's go ahead and put 1 over x, x prime we'll call it. And call that 1 over x. Okay? X prime equals 1 over x. And so I just put in the x with the reciprocal, 1 over, right? 1 over the x. So there's the new regressor. That looks pretty simple, right? And then I'll just go ahead and regress y and 1 over x. Tools, data analysis, regression. Simple linear regression of y and 1 over x. Input y range. Input x range. Okay. Labels, output range, residuals. Line fit plot. Okay, to see what happens here. Output range here. Okay. Okay, so there's a straight line fit. It's got a, okay. So it looks halfway decent, right? Okay? And so now you're getting beta 0 is about 3, which makes sense. If you look at the picture, the original scatter plot, the asymptote could have been about 3. Okay, in terms of DC output, I'm not sure what units that was in. DC output, he's got units 1, 2, 3 on the y-axis. Okay, so my intercept is coming out about 3, 2.97. Right, and then I have this. The beta is negative number as I predicted it should be. Okay, and so there you have it. Okay, and so that's interpretable in terms of the model. So because you don't have to change the y values. Okay, you just have to change what your actual x is, so that you can sort of interpret the betas. Okay, in some sense. So you can predict y in its original units in this situation. So that's actually an easier kind of fix, as long as you can find the right transformation. Now, was y equals, is that the right one? Beta 0 plus beta 1 times 1 over x? How do you know it's the right one? What's the best? How do you actually? You can study the residuals, see if everything is kosher and everything like that, I guess. Okay, so we can do some residual plots and so on and so forth. But what's another method? If you didn't have any idea, you just know there was an asymptote, but you didn't know, why should it be power 1 over x to the minus 1? Beta 0 plus beta 1 x to the minus 1. Is there any method, numerical method, where we might try to figure out what the exponent would be? That would bring in another parameter. So now what we'll do is we'll try to play a game where we try to bring in another parameter in a non-linear way. So this brings in the question of how to deal with that. So let's do a little bit of mathematics about that. Okay. We're going to have to keep switching back to the picture, unfortunately, but suppose I now have a model of the following form. Suppose how to estimate alpha when we assume a regression function of the form beta 0 plus beta 1 x to the alpha for the windmill data. How can I do that? What would be a method?
Well, you want to minimize alpha, right?
Well, presumably alpha is less than 0, where alpha is less than 0 from the picture, right? The question is it minus 1/2, minus 1, minus 2, minus 3?
You still want to minimize your mean square residuals. You still want to have the same goal, basically.
Yeah, you want to still have the same goal. Now, what should it be, though? How should I have it? How should I play this game? In other words, I have alpha. I should start nearby maybe something that's the right alpha and try to adjust it. Okay, so here's what we're going to do. We'll start with alpha 0 equal to 1 plus 1. Okay, it's not even negative yet. Okay? And try to figure out a new alpha by an iterative procedure. Okay? Estimate beta 0 and beta 1 by a simple linear regression. Which we did. And I do believe that the beta 0 and the beta 1 were equal to, I have to check here what they were. For this simple linear regression, the beta 0 and the beta 1 were 0.1309 and 0.2412. Approximately. And that should jibe with what was in the text. I'm not sure if they reported those or not. Okay. Yes, that was on page 182. I think he truncated the digits on page 182, but that was the simple linear regression fit. Okay? That's the first step. You do that. Then, how would I get an approximation to this function? Okay? How could I get this? What I'll do is a Taylor series in the variable alpha. Okay? So what I need to do is I'm saying that if I have this EY. Okay, so now I'm going to fix beta 1 and beta 0 and beta 1. I'm going to do EY is approximately equal then to beta 0 plus beta 1x, where I'm going to take my beta 0 and beta 1 given by those numbers. This is really applied math. Okay, plus alpha minus alpha 0 times the derivative with respect to alpha of beta 0 plus beta 1x to the alpha. So I'm treating alpha as the variable, and I'm writing this as a function of, I'm thinking of E of y as a function of alpha and making a linear approximation in alpha to that function near alpha 0 equals 1. I'm not even bothering with anything else, okay, because this is already linear in beta 0 and beta 1. So I want to approximate EY as a linear function of the parameters. There's 3 parameters now, beta 0, beta 1, and alpha, and I want a linear function of the 3 parameters. Okay? So this is a linear function of the 3 parameters because this is at alpha equals to alpha 0. I'm going to plug that in, so that's going to be a number. So what does that come out to be? What is the derivative of beta 0? Well, that's going to be 0 as a constant. Beta 1 will come out. What's the derivative of x to the alpha with respect to alpha? X to the alpha with respect d by d alpha x to the alpha. How do you do that? No. If x is the variable, it's alpha x to the alpha minus 1. So you have to write this as d by d alpha e to the alpha log x. Okay? Then take the derivative with respect to alpha. You get a log x coming down. Okay? And then you get your exponential back again, e to the alpha log x equals log x times x to the alpha. Okay? And now I'm going to plug in alpha equal to 0. So alpha 0 equal to 1. So if I get d by d alpha x to the alpha at alpha equals to alpha 0 equals to 1, I get log x times x to the 1 equals x log x. Okay, that's the derivative there. Okay, so what I get is that this EY is approximately, therefore, equal to beta 0 plus beta 1x plus alpha minus 1, alpha 0 was 1, times x log x. Interesting, huh? Okay, that's a linear approximation to this function in terms of the parameters beta 1, beta 0, beta 1, and alpha. So really what I needed is that, I needed a linear expression here. So now what I can do is I have 3 variables, or 2 regressors, x and x log x. And then what I can do now is do the multiple regression. I'm sorry, I forgot my beta 1 here. So I do multiple regression, and I'll now get new estimates. Okay? So now I'll do multiple regression. You say, who thought this up? Okay, multiple regression. And I'll just call this parameter gamma. All right? I'll just call this beta 1 times alpha minus 1. I'll call it gamma. And I need to estimate gamma, and once I estimate gamma, then I'll divide by beta 1, and I'll add 1, and I'll get my alpha. So, do multiple regression, obtain. Now I'm going to obtain a new beta 0 hat, a beta 1 hat, and a gamma hat, right? So I'll call it obtain beta 0 hat new, or updated. Okay, and a beta 1 hat updated, and a gamma hat. Okay, and I'll say do multiple regression of y on x and x log x. So I have 2 variables, x and x log x. All right, and I get a beta 0 hat updated, a beta 1 hat updated, and a gamma hat. Now what I'll do is then say that alpha 1, my next approximation alpha is going to be therefore gamma hat, but I have this beta 1, the old beta 1 in here. Okay, so I'm going to use the old beta 1 here. Gamma 1 hat divided by the beta 1 hat, the old one. Previous, I could call it, or old. Previous one, because that's what I had in this equation, right? Plus 1. That's my new alpha 1. Or my new alpha. Okay? Then I can go through this whole thing again and get a second alpha, and let's see what happens. Just getting the first alpha, what happens? What I've done now is turn the picture on. Okay, that's the original fit that didn't fit. Okay. Okay, now what I've done, I've taken x log x as another variable. And now I'm going to do regress y on x and x log x. And here's what I get. I get this summary information over here. Okay. So I get from my gamma hat negative 0.46. For my updated beta 1 hat 1.53. My updated beta 0 hat minus 2.4. So these are the updated beta hats. All right. But my gamma hat, my alpha hat, or alpha 1. Okay. He's calling the text alpha 1 because I had an alpha 0 equals 1. Now I have my new alpha is 1 plus gamma hat over the old beta 1 hat. Okay? Which is the 1 plus the negative 0.4626 divided by the 0.24115, I guess it was. Equals negative 0.91. He got a negative 0.92 in the text. I don't know how he did that. I got negative 0.91. Okay, so that looks like, hey, that looks like I'm done, right? I got something very close to negative 1. But what if I do it again? Well, I get negative 2 or negative 3. I think there's some argument in the book that this procedure converges readily. Okay, if it's going to work. So how would you do it again? And here, well, here it is. Here's now these are the residuals for the transform windmill data. So I've regressed y now on x prime equals x to the negative 0.91. Okay, and then I got the residuals here. They look halfway decent. Okay. What happened? I don't know if I do it again here. No, I didn't. Okay. What you can do is you can do a second step and see what happens to alpha. Let's look in the book and see what he says about that. This is and double check what he's doing. Procedure he's doing is correct. To perform a second iteration where we define a new regressive variable, x prime equals x to the negative 0.92. Well, I put negative 0.91. For some reason, we differed a little bit on how the alpha came out. Read on the bottom of page 192 of the text. To perform a second iteration, we would define a new regressive variable, x prime equals x to the negative 0.92, which is exactly what I did here to check whether the residuals look any decent. And they did. They look decent. But maybe they could even be better. Okay? Okay. So then you would have the then you have these regression coefficients, beta 0 hat and beta 1 hat for that model. Okay. So well, they're not the same as the updated ones that I had, because that was with a multiple regression. So now I just go back to just a regression on 2 parameters to figure out what the old beta hats are going to be. So I get new old beta hats by putting in the value alpha 1 for alpha. All right, so let's do this. So now I go back and I'm going to have y equals beta 0 plus beta 1 x to the negative 0.91, in my worksheet it would be, plus, okay, let's see, is this right? Would give me the baseline again now. Okay, so I'll get a beta 0 hat out of that. This gives beta 0 hat equal to 3.118, and it gives beta 1 hat equal to negative 0.66. Excuse me, negative 6.66 in something else. Okay, there the 666 is. Ooh. Okay. That's not really 666. Okay. 665. Okay. So, does that match with what's in the book on the bottom of page 192? I believe it does. Close. He has 3.104 and 6.67 or something. Okay? Because it's slightly different alpha 1. Okay? A little rounding error there. So now what I'm going to do is then I'm going to say, okay, EY, or this is EY, and then I'm going to take EY is approximately equal to, now this beta 0, and this beta 1, I'm not going to put the hats on there, plus beta 1, x to the negative 0.91 plus alpha minus alpha 1 d by d alpha x to the alpha at alpha equals to negative, alpha equals alpha 1 now. Okay? So what I'm getting is then beta 0 plus beta 1 x to the negative 0.91. That's my first regressor, x to the negative 0.91. Plus, then I get alpha minus the negative point, plus I'll just put 0.91. Okay. Times the derivative of this, which we said was log x times x to the negative 0.91. Because I have to put, you get log x times x to the alpha, and then you have to put your alpha equals negative 0.91 in. So then I have two regressors again, but now it's x to the negative 0.91 and log x times x to the negative 0.91. Okay, so I could throw this in and see if we get the same answers as he does. Okay? So what I do now is I need to take this and I need to put in another regressor. Okay? Which is what? What's the other regressor I need? What happened? Okay, there we go. I need to put in a second regressor, so I need to leave room for that. It'll be log x times this one. It'll be log x times x prime. Okay? You just multiply by log x. That's my second regressor. No, it doesn't matter if I, now I better put in log x. Uh-oh. I need to put my x in also. Let's cut all these over, because I don't want to put in log of x prime, otherwise I'll get the wrong regressor. For this thing. There's maybe more than one way to do it. I just want to make sure that we get it right using this method. Okay, so if I want to do it again. Alright, so now I can put in the formula for log x times x prime equals log of this one times this one. So that's my second regressor. Okay, now let's do the regression of y on these two regressors. That's going to give me an updated, well, it's going to give me an updated beta 0 head, beta 1 head, and so on, but it's actually only for the multiple regression model, so it's actually not useful because it's not the same as these. Okay, these are the ones, I really probably shouldn't have called them updated. These are the ones I want to look at. Okay? So now, do the multiple regression. Is everybody kind of following what I'm doing here? Sort of? I'm trying, I fit these, and now I'm trying to get the correction, because this is maybe not the right exponent. So this is the correction term. Okay? And so I get that this is now the right regression function. Okay? Approximately. As a linear function of alpha and the betas, with beta 1 equal to that number. Okay? So obtain. Do the regression. All I'm looking for is the coefficients, right? So all I'm looking for is the gamma, really. So let's go ahead and get that data analysis and get the gamma. So, darn it, I've got to go searching for it. Okay, here's the y variable. I put the x variable in. Both of them. X to the negative 0.91 and log x times x to the negative 0.91. I put negative 0.9. I don't know what that. I must have cut it off. Okay. I'll put range. Anywhere in here will work, right? Okay. All I care is that here's my negative 0.495 for my gamma, right there. Gamma hat. So therefore, now, what do I have? I've got gamma hat equals negative 0.495, and that's, on the other hand, that's equal to the beta hat, which is the beta 1 hat, which is the negative 0.66 business, 6.66 times alpha 2 minus 1. Therefore, alpha 2 is equal to negative 0.495. I'm sorry, plus, this is plus a 0.91. So, negative 4.495 over the negative 6.66. I have it right. Alpha 2 is the other way. Divided by 0.4. Minus 0.91. This doesn't look right. Something's messed up. I'm not dividing it right. Negative 0.495 divided by negative 6.66 puts it on the other side. I'm just trying to solve for alpha 2. Alpha 2, okay, minus 0.91. Okay? That doesn't look right. Where's my negative signs? I'm sorry, I got my gamma hat coefficients came out at negative 0.49479. He's getting a plus 0.599. I think I made a mistake here. How did I get this? Second regressor, x prime log x prime. Ah! Okay. Yeah, okay, you got to be a little bit careful, because I've got x prime. Yeah. This is log x to the negative. There's a negative 0.91 in here, I believe. Log of x. Yeah. Oh no. Is that right? I'm missing a negative 0.91 somewhere. Yeah. It must be. Wait a second. Let me check this out. What is the derivative of x to the alpha here? Something looks fishy. Something looks fishy. I'm sorry. What's the derivative of x to the negative 0.91? D by d. I'm sorry, it's x to the alpha. Ah. Yeah, that's right. Equals log x, x to the alpha. Okay. Well, he's doing something a little different. Okay. But it's got to come out in the wash. Okay. So, because he's putting log of x prime times x prime. Okay. Is getting that. No, we shouldn't have tried this by hand. Okay. So what should I get? I should get gamma. Oh, this is plus a beta 1. I should get beta 1 times, according to what I'm doing, what am I doing here? I get alpha plus 0.9 times log x to the negative 0.91. That's what I have here. And so how did I have the beta 1 before? Okay. I'm doing it a little bit different. What am I doing here? I think it might be how I set up my propagation problem. Let's see. Oh, yeah. Plus alpha times beta 1 log x. Yeah, there was a beta 1. D by d alpha, beta 0 plus beta 1 x to the alpha. I see. Plus, I should have had d by dx beta 0 plus beta 1 x to the alpha. Okay. Yeah. Okay. So that would give me a beta 1 here. Does that make a difference? Beta 1? Yeah, I already have that. Okay? Okay. Yeah, that's right. X to the alpha. So then regress on those, and I should gamma equals beta 1 times alpha plus 0.9. All right, I seem to be making a mistake. That doesn't look right. Minus 0.9. Well, I guess I could try it. Doesn't look right, though. Because that's going to give me something which is bigger than negative 0.9. Okay. So I'm going to have to skip it here and correct that later, it looks like. Unless I did something wrong with my alpha. I don't think I did something wrong. I'm still getting beta hat as negative 6. Okay, which is right. Okay. Then I'm getting my gamma as this. Okay, and the only question of what's the right relationship. Okay, the right relationship was alpha hat is 1. So now it should be alpha hat. I must be doing something wrong. Alpha hat plus. I'm getting the minus signs wrong or something like that. I should be getting alpha 1 hat plus this business. Okay, over the old beta hat. Oh, old beta hat. Yeah, that was the negative 6.66. The gamma hat, the problem is I'm getting a gamma hat as a negative 0.5 instead of a plus 0.5. That seems to be the problem. And that's because I put in something funny here, so I'm not seeing how to get out of that trap. Sorry. This is going the wrong way. So I've got a mistake in here somewhere. Either that or I'm right and he's wrong. Because he wanted to get his x equals minus 1. So I would want to see if this converges. I need to take it a couple more steps and see if it's converging to minus 1 or something else, minus 0.8. Right? I need to see if it's converging to minus 1 or minus 0.8. I need to see if it's my error or his error. Okay? So let me skip this for now. Okay? And I'll have to correct it next time. Is it going to minus 0.8 or is it going to minus 1? He seems to have gotten it go to minus 1. All right? So we have a numerical issue that I did not prepare. Excuse me. Does everybody see the problem? Okay. I'll fix it next time. Okay. Let's go on. What else can we do? We're not going to be able to get it today from all the mess-ups. What we want to do next is consider the case a different approach, a slightly different approach to the case of non-constant variance. Here we did have constant variance. We just had the wrong regression function. We were trying to find a regression function by hook or by crook, okay, that had a non-linear parameter. All right? You had beta 0 plus beta 1 x to the alpha. So here's a game they were playing by iterated process to try to figure out what the actual alpha is. So a nonlinear, certainly a nonlinear regression function. That wasn't the point, though. The point was that the regression function was nonlinear in the parameter. Okay, not nonlinear in x, but nonlinear in the parameter. We can fit nonlinear regression functions as long as they're linear in the parameters. That's not a problem. And then we guessed beta 0 plus beta 1 times 1 over x. Hey, all was good. But if you actually start looking at it, then you get into an iterative procedure to figure out what alpha is, which we kind of blew at the end there. But what happens, let's change the subject, what happens if now you have yi, so I want to get into something called weighted regression, weighted least squares. The last topic in this chapter. What happens when yi is equal to, or y is equal to x beta plus epsilon, where again you'll take uncorrelated epsilon I, covariance between epsilon I and epsilon j is equal to 0 for I unequal to j. But what I'm going to do now is I'm going to take the variance of epsilon I to be sigma squared divided by some wii. Okay, so I'm going to take the variance covariance matrix of the epsilon to be of the form V equals sigma squared times 1 over W11, 1 over W22, and so on down to 1 over WNN. And 0 off diagonal. So it's a diagonal variance covariance matrix, but with unequal entries along the diagonal. And we're going to study this specific example for for weighted least squares. We're going to skip generalized least squares and only consider this very special case. I'm sorry, this should have been sigma squared V, the way he looks at this. Okay, bottom of page 195. Okay. What could you do? How could you transform the variables to make error variance constant? If you simply have this, simply just have the variances are 1 over wii times sigma squared. What you can do is you can simply define z. So you transform both y and x. Define z equals to zi equals the square root of wi. I'm sorry, this is not an I only need a one index for these w's. Okay? wi times yi, and I take, I don't change the betas at all. I'm going to define new regressors uij equal to the square root of wi times xj, where x0 I'll take to be x0 is the column of ones, the intercept. Okay. And now I'm going to come up with new regressors, uj. J goes from 0 up to k, but none of them might be a column of ones. So I'm going to do like that. This should have been xij here. All right. So there's going to be new columns just by multiplying each of the old columns by the square root of wi in the ith place. So I'm going to take my x matrix, which was equal to 1, 1, 1, 1, 1, 1, like this, x 1, 1, x 2, 1, down to xn 1, and then over to x1k, down to xnk. And I'm going to convert it into a U matrix by multiplying each row by the square root of w, the corresponding square root of w. So I'm just going to get the square root of w1, square root of w2, down to square root of wn. I'm going to get the square root of w1 times x11, square root of w2 times x21, down to square root of wn times xn1. So I just changed the column. So I'm multiplying two columns, right? I have the square root of, I have the w column and the square root of w column, and I just multiply square root of w1 times x1k down to the square root of wn xnk. So if I do that, I call this, he calls it capital B, but I think that was a poor choice because of the regression coefficients being so close to B's. Okay, I call it capital U. Right, changing x's to u's. So this is what I call the column U0. This is the column U1. This is the column UK. So we get k regressors, k plus 1 regressors. None of them are the constants. 1, 1, 1, 1, 1, unless, it turns out in a special case that they would be. And there is one special case in which it is, which we'll have to discuss next time, which is kind of interesting. And then my epsilon. So what happens if I've got if I do that, and then I just go ahead and take epsilon equal to, or I just change my errors by calling delta equal to the square root of wi epsilon. Okay. So what I have y equals x beta plus epsilon, and all I'm going to do is I'll multiply by this matrix, which is multiply both sides by, and I'll quit here after I get this equation, both sides by the following matrix. The square root of w1, it's a diagonal matrix, square root of wn. And what does that do? It converts the x into the u, it converts the y into the z, and it converts the epsilon into the delta. Then I get z equals u, the beta stays the same, plus delta, where now delta has constant variance, sigma squared. The variance of delta I is the variance of the square root of wi times epsilon I equals wi times sigma squared over wi, because I put the square root of wi squared, because when I multiply a constant times a variable, underneath the variance sign it comes out as the constant squared. So the wi's cancel, and that's why we chose it that way. This is just a particular parameterization. Why do they choose 1 over w is for the variance covariance matrix, and therefore multiply by the square root of w is just the way somebody thought of to do it, and so we'll stay with the program. Particular parameterization. So then what you do is you simply transform everything, get your y's become z's, your x's become u's, and you regress z on the u's. Okay? And the betas are the same as they were before. Okay? And so those are the weighted least squares estimates of the betas. So that's kind of nice. You have that situation. And we could have done the same thing with that Poisson data. Okay? By an iterative process, we don't know exactly what the weights are first. You have to iteratively re-weight. Because as you change your regression function, the weights would change. The mean, right? The variance was the mean, right? So as I start to adjust what my parameters are, the mean changes, right? and then it converges. So then you weight it, you calculate the betas, you go back and figure out what the weights should be again, because the weights correspond to the variance, and the variance was equal to the mean in the Poisson data. So then you get some new weights, all right, and you get some new betas, and you keep doing it a few times, and pretty soon it converges. And so you could do that Poisson data by this weighted least squares approach. All right, so maybe I'll do that in iterative procedure and see how that comes out. All right, so that way you don't have to worry about squaring at the end. You just get your betas out straight up. Okay. Okay. Why don't we quit there? And I'll do some more computing. You can see how there's a lot of computing in here. If you have to do several pages now if you're going to do these iterative procedures. So it's a lot more computing intensive. All right. That you can have that last week when I'm gone. Okay. To do some of these. All right. You still have time when we come back. All right. Thank you.